everyone can build his own system that can do extreme performance for AI and high performance computing. This is why many are trying to move high performance computing to the cloud so that companies can build those large computers and rent cycles on the supercomputers, which means we need to move to a cloud-ready kind of technologies, and implement even in-network computing now has to go to some kind of virtualized environment or some kind of multi-tenant environment where, you know, those trees that are now running on switches needs to be shared between multiple tenants, needs to be shared between multiple users, and we need to be able to build those trees, those aggregation trees, in a way that can be used by multiple users and multiple tenants with isolation in both performance and data isolation. You don't want one tenant to access the other tenant's data, and you don't want one tenant or one user to suffer from someone else's workloads. You want to get your performance regardless of what the other users are running. So this is for in-network computing, one technology. Another interesting component and very important component in this high-performance in-network computing is the DPUs, the data processing unit. The data processing unit replaces the good old network interface card, the good old NICs. What it does is it provides you the network interface functionality that used to be in every NIC, but it adds to that programmable compute cores that enables running the data center infrastructure. Right? We talked about that earlier. We need to move the data center infrastructure software from the host CPU that runs the application to free up those cycles, to free up the caches, to free up the resources on the CPU or GPU. So one thing is running the infrastructure on these programmable compute cores. On top of that, we accelerate the infrastructure by some hardware acceleration engines. Just an example is if you want to run security and you need to encrypt and decrypt the data, it's way more efficient to do that with hardware acceleration and not just CPUs. And we will discuss in more details the usage of data processing units in specifically high-performance computing later this week. So let me skip one slide. Beyond just accelerating the data center infrastructure, it actually enables accelerating applications. The application that runs on the host can be accelerated by using DPUs. A very high-level example would be, let's say that you need to do message pathing, collective communication. You can actually offload the progress of whatever communication it is that you're using into these DPUs so that you have asynchronous progress running on your DPU, data processing engine, while the application is running on the host, on the CPU or GPU. So the application is running, and at the same time, the DPU is responsible for data movement, for collective communication, let's say reductions or all-to-all kind of communication. All those communications can run in an asynchronous manner while the application is running on the CPU. So that when the application will need the next stage of data, the data will be ready. Probably the most inefficient way or the most expensive thing for a CPU and GPU to do is just wait for data. So we want to make sure that when the CPU, that the CPU and GPU will always have data for processing. No, I'm not going to go through those details. We have a session specifically for that. But again, at very high level, the idea is that the host can offload some functionality to a DPU, indicate that, hey, I need you to do something to implement some communication scheme. The CPU now can go to the application. The DPU will do all the work, all the progress of the communication, and when done with the communication, it will notify the host, your data is ready, go ahead and keep processing. Some important thing to notice, we are going to talk about HPC and AI. We are going to focus on the networking and communication part. One may ask himself, why do I care about communication? Why do I want to spend the efforts on communication? I want to talk about computing, right? I do computing, I want to do some matrix multiplication. Why do I talk about networking? And the reason is that the application is spending tons of time in communication. The reason is that scaling to a very large number of processing engine inherently adds overhead of exchanging data. Getting the data to the processing engine is probably the most complicated task that we need to do today to actually enable efficient utilization of processing engines. So you see some applications, and you can see the amount of time spent in communication. In this case, it's high-performance computing applications using MPI. And it's interesting to see first that a very significant time is being spent in communication instead of computation. And when you look at the communication, we see that some of the, you see the highest cost operations. We see basically that all-to-all, all-reduce, broadcast are the application that take most of the time. And again, we will discuss all-reduce specifically and all-to-all in details. We might discuss broadcast. We will see how time will allow. And also there is some point-to-point communication here, NPI receive and NPI send receive. We will spend some time on that as well. So allowing high-performance computing requires efficient communication. Otherwise, it doesn't help that you buy the highest performing GPUs and connect thousands of them if they just wait for the data. It's not a very efficient way to utilize the resources. Now, I'd like to move to UCF. UCF is a consortium that took the challenge of standardizing communication frameworks. There have been multiple coming from different companies. I'll show that in a minute. Where the focus here and the interesting part of UCF is that we understand that we need software protocols and we understand that we need software APIs, but we need to understand that to really go to the scale and performance that we need to look at hardware transports as well and the hardware offloads as well. And we need to build these co-design between software and hardware, between new protocol and old requirements, and figure out how we build a scalable framework so that we don't need to change that every other year. We want something that will take us to the next decade with software protocols, with hardware transports, and with scalability that allows us to keep getting the performance we are looking into, which is very challenging. So UCF is, as I said, is a consortium that took this challenge of building APIs, building frameworks, building software libraries that will enable communication for high-performance computing, for machine learning and AI, for storage, for different data center problems, all under the same umbrella, with different collaboration from industry, laboratories, academia. And I think, at least from my experience, is that we had great success in some directions. Some directions are still very early and will need collaboration. And I invite everyone that is interested to take a look and join the different working groups. I'm not going to read the board members, but you can see that it's being led by national lab, universities, industry, companies that care about communication, that care about processing, are driving those the framework and the consortium. The consortium includes multiple projects. I'd say for this week, two of them are the most important. One is the UCX, Unified Communication X. This is the basics of data delivery technology. You know, we will talk about TCP and we will talk about RDMA, and we might talk about different transports for RDMA. We would like to unify everything under the same umbrella and create shared APIs so that even if today you use one technology and you build your application on top of that, in the future, if a new transport is being introduced, you don't have to change the application. We want to make sure that you will take the latest UCX library, you will use the same APIs for your application. UCX is deployed in many installations, and I'll try to talk about that later. The second one that we will focus this week is UCC, the Unified Collective Communication Library. If UCX is the basic of data communication covering point-to-point communication, UCC extends the UCX capabilities into collective e-communication, where more than two participants are participating in the data exchange. So you will see, again, we will talk about reductions, all reduce, and actually a part of the hackathon challenge relates to UCC. I'll introduce that later today. And there are some other projects like the Spark UCX, specifically for Spark, OpenSnappy for SmartNIC projects. It's actually a try to expose data processing unit in an abstraction layer to data processing unit that will enable, again, easily utilizing SmartNICs, while at the same time allowing each vendor of SmartNICs or DPUs to add his extra capabilities, extra transport accelerators, so that on top of the OpenSnappy, if you write your application on top of that, you will be able to use different SmartNICs. You will be able to easily move from one generation of SmartNIC to the next generation of SmartNIC. Just like UCX did for data transport, OpenSnappy is working on DPUs and SmartNICs. I'm a co-chair of the OpenSnappy, so you will see that I'll probably talk about OpenSnappy more than once this week. And there are other projects, and the UCF umbrella allows us to bring new ideas, create a working group. If the working group materializes to something that people can use, we will have those projects with open source code and allow everyone to contribute. So UCX, as I said, is the point-to-point communication library that started in some conference where people met and understood there is a need. And maybe the most important is the history of how it happened. So going back in time, it started with the Los Alamos MPI and other codes that had to implement communication. So Los Alamos National Lab had their own LA MPI that at some point when was replaced by OpenMPI, a more open and modular architecture for MPI that had its own transport for communication. At the same time, there were different libraries coming from different vendors, like MXM coming from Mellanox, and I don't remember who, PAMI coming from IBM. And all those teams realized that instead of having those competing technologies and competing libraries, we can have best in class one library that merges the knowledge and the experience and the challenges that all those teams had before. So uniting the forces into UCX gave us what we have today. It's a mix of architectures, it's a mix of experiences, it's a mix of knowledge that came into UCX to build the best-in-class communication library. And you can see that today many are using that so to make sure that it's available for everyone. UCX supports different architectures from host memory. It supports x86, ARM, and Power. From GPU memory, it supports ARM and NVIDIA. It supports DPU memory. So it's not limited to one vendor's technology. And it's being used for different type of communication schemes like MPI and PGAS and ML and AI frameworks like TensorFlow and PyTorch, data analytics, storage, GPU APIs. So the idea is to build this abstraction layer that can be used by everyone and that can be optimized for everyone and can run on any type of hardware that you would like to use. It's not limited to one vendor. It's not limited to one use case. And this is UCX. I'm not going to go through the architecture. You will have deep dive into UCX and you will use UCX. So let me skip that one. In terms of users, I already said the idea is to try and have wide usage instead of everyone building their own communication library, so that everyone now can contribute into this open source project and utilize it instead of having different teams optimizing their own libraries. That includes MPI implementation, so you can see a long list of MPIs using UCX as the communication layer. Beyond MPI, we have PGAS, GASNet, we have OpenSHMEM. Again, multiple OpenSHMEM implementations are actually based on UCX. And beyond that, we have the Charm and Rapids and NVIDIA Nickel, and there are actually some more that are not here. Some of them are public, some of them are not even public, where companies can take UCX, use it in their own needs, and they don't need to report that to anyone. So UCX is used in more than I know applications, and I know a long list of applications. So you will have those slides, so you will have access to the code, to the website, mailing list. And again, if you are going to work on communications, I invite you to join them. Join the team and contribute or follow what we're doing in UCX. Beyond UCX, we have UCC, as I said, the collective communication framework for collective, again, open source projects, providing APIs to collective or group communications for MPI, for artificial intelligence, for data center, for IO storage, and many other types of applications. And it's leveraging hardware topology awareness, software implementation techniques, in-network computing co-design. All of those are built into the UCC architecture so that if any vendor comes with a new hardware acceleration for some specific communication scheme, it's very easy to integrate that into UCC and use that, so that eventually UCC should, just like UCX, work on any hardware technology from processing engine side, x86, ARM, PowerPC, whatever, probably RISC-V at some point. And it should work for any type of application that requires collective communication. So again, you will have deep dive into UCC. I'll actually skip the high level for now. And I want to go into what we're all looking for, the 2023 RDMA programming lecture and hackathon. This is what you're all in here for, sorry. So let's start with the great instructors that you will have. This is just the highlights. You will have more than that. We have great people. Well, most of them, I'll skip the first one, but most of them are great instructors that are here for you to give you access to knowledge, to give you access to best practices. I hope you will all enjoy the lectures and you will all have the opportunity to ask questions. So I encourage you to ask questions during the lectures. After the lectures, we will have time allocated for questions. Take advantage. It's not very common to see this kind of list of lecturers coming from different centers, different universities at the same location. Use this opportunity to learn, to ask questions. I'll go through this list. I'm the first one, so I'm not going to talk about myself. We have Dr. Zidong from, who is a professor in the computer science department of Tsinghua University. Dr. Manjunath from the AI, HPC and AI Advisory Council, who's also a co-chair of UCC work group. So again, we're going to talk about collectives. And the hackathon is actually relates to UCC. So use the opportunity to talk to him. He's also a previous research scientist in computer science and mathematics division at Oak Ridge National Lab in the US. We have Dr. Rich Graham, chairman of the MPI Forum, founder of OpenMPI. You know, he is, I'd say, the father of MPI. He's been there for many years. He used to be a distinguished member of Oak Ridge National Research Team. Again, his experience in MPI's communication is second to none. We also have Dr. Wenfei Wu, assistant professor at Peking University, and Dr. Hold on, I'm sorry about that, and Dr. Yujun Zhang, and I'm sorry for the way I pronounce name. It's kind of hard for me. Who's a research professor and director of Parallel Software Laboratory, Institute of Computing Technology, Chinese Academy of Science, also Secretary General of CCF, TCHPC, and Chair of ACM SIG-HPC China. So again, this is just a part of the list of instructors you will meet during this week. Hope you benefit from this opportunity and access to knowledge and experience. So about you, we have more than 50 teams. We actually have a team that joined after we created this list. So more than 50 teams participating in this week, in the lectures and hackathons. We have 10 teams from the industry. You can see the list. I'm not going to read that. And more than 40 universities and research centers. So first, thank you all for joining. I'd like to wish each and every one of you good luck. I hope you all enjoy this week. I hope you all learn a lot during this week. And what you are going to see, so the lectures include RDMA, network computing. I'm not going to list the lectures. On top of that, you will have the programming competition, the hackathon. And in the hackathon, you will have an opportunity to develop an operation on top of SHARP, on top of e-network computing. SHARP is the technology that allows to do e-network reductions. What we're going to implement is basically reduce scatter. I'll discuss what reduce scatter is in details later. So if you're not familiar with that, don't worry about it. We will discuss that. The reason we will focus on reduce scatter is that AI applications have been using all reduce operations for a long time to allow distribution of the problem on multiple processing engines. With the large models, specifically large language models, but not only, all the large models require new techniques to optimize so that we can scale to, tens of thousands of GPUs. And reduced scatter is a part of it. Again, I'm going to discuss why reduced scatter is important. I'm going to discuss in detail what reduced scatter is. So if you're not familiar with the terms, don't worry about it. Just remember what we're doing here is not solving the problems of last year, but solving the problem of next year, enabling scaling of AI to the new requirements. And last thing, if you want to contact the HPC and AI Advisory Council, you have the links, you have the social media. Please feel free to contact if your organization would like to join. If your organization would like to join the HPC and AI Advisory Council, you have a way to do that. And we encourage you to do that if you haven't done that before. And with that, thank you. This was just the opening, and I hope you will all enjoy a very productive week. With that, let's take a 13 minutes break. 10 minutes. Yeah. 13. So 13, so we meet on the hour. Yeah. Let's meet again at 10 a.m. China time zone. If you're, it's not, sorry, it's not 10 a.m. Sorry, my bad. 3 p.m. Yes. My bad. I was looking at the wrong time zone. Let's all meet at 3 p.m. for the next session. It's going to be me again. So I'm sorry about that. If you didn't enjoy the first one, hope you will enjoy the next. So see you all in 3 p.m. By the way, if anyone has questions, you can ask them now. Thank you. Okay, so I'm back with a different topic now. I'll start by answering the question in the chat. I don't see the chat now, but I read it before. So I saw that the question was whether UCC is replacing MPI as a collective communication library. So the answer is no. The idea is not to replace MPI, but if you look at MPI implementations, instead of implementing collective communication, they actually use UCC. So if you wrote your application on top of MPI, you do not want to change the application. What happens is that modern MPI implementations, instead of implementing all the collective communication code, all the algorithms, they actually call UCC. And this was the idea, not to give an application layer abstraction APIs, but a lower level, so that the same UCC is now used by anyone who's using MPI applications. It can also be used by anyone using AI applications that require collective communication. There are some cases where AI applications are using MPI, but it's not that common. Most of them are not. So if you look at, let's say, PyTorch, you can use PyTorch with UCC directly. So your API is actually PyTorch, but then it uses UCC. Same for different programming models. Same for PIGAs or OpenSHMEM kind of programming languages and programming schemes. They all use the same UCC infrastructure. So you can implement the collective algorithms once and use them in all the kind of different applications. So specifically MPI, if you look at OpenMPI, it is using UCC. If you look at other MPI implementations, you will find out that they are all using UCC today. Let's see, I see there is a new message. Okay, let me read it first. Let's ask a question about MPI RDMA and contiguous communication. Okay, it's a very interesting question. Let me answer that later today. I wanted, before I get to how we can do in-network computing for non-contiguous data, I want to build the background, and I promise to come back to this question. If I don't, please remind me, and I'll discuss specifically that. So for now, what I wanted to talk about is the future of computing, with obviously the focus on supercomputing. You know, this is a computer, and I don't want to discuss the future of cell phone computing. It's not interesting in the context of this talk. My focus, I wanted at least to build a presentation discussing the future of supercomputing. Hold on, let me have my laser pointer before we go on. Okay, but the problem is that talking about the future is always problematic. A very short story, which is not related to the topic we're talking about, is about Cassandra from the Greek mythology. And the story is short. Cassandra was the daughter of king and queen of the king and queen, and she was at the temple of Apollo. Apollo fell in love with her, wanted her to be with him. She refused, or at first she said yes. When she said yes, Apollo gave her the ability to predict the future. And she became a very known person, but then she did not agree to live with Apollo. So what he did, instead of taking her ability to predict the future, was to make sure that no one will ever believe what she says. So she could predict the future. No one believed her. She was the daughter of king and queen of Troya, the city, and hope you're familiar with the Trojan horse. What happened was that she predicted that the Romans will come with the Trojan horse and will have soldiers inside the horse. She told her parents, the king and queen of Troya. They didn't believe her, and we all know what happened. So instead of talking about the future, and again, I am going to predict or try to predict the future. Please remember that I don't really know what's going to happen in the future. It's a prediction, and most of the time in this talk, I'm actually going to talk about the past. And I'm going to talk about the past and show you why I believe the supercomputing in going into a specific direction. And hopefully you'll be convinced. Some of the trends and some of the things that are happening that I'm going to predict are actually happening today. The future starts today, and we're working on that. So instead of talking about the future of supercomputing, let's first talk about trends in computing and communication. I don't know why I have this line. I'll try to clean that later. So again, I'm going to talk about multiple trends. None of those trends will be new to you. I'm quite sure you've heard and you're familiar with these trends. But the reason I'm putting them here in this presentation is to build the background that is needed to actually see where we need to go with supercomputing. The first one is Moore's law. Hopefully you're all familiar with Moore's law. Gordon Moore, who predicted that the number of transistors and resistors on a chip will double every 24 months, actually predicted that, and later he updated that so that it's not 24 months, but it's 18 months. And if you look at the industry, it actually held for a long time. To be honest, it still is sort of true today. The problem is that most people, when talking about Moore's law, don't talk about the number of transistors. I don't care how many transistors I have in my CPU or in my GPU. That's not what you're buying. Yes, you're paying for transistors, but actually what you care for is performance. And the interesting part was that if you look at the history, yes, the number of transistors was doubled anywhere between 18 and 24 months. It was also true for performance. And this was the important part. You knew that if you wait for 24 months, you will get a CPU or GPU or processing engine that will have double the performance of what you had 2 years ago. And you could expect that it will keep growing, and you have larger problems you would like to solve. You just need to wait enough time to have the CPU with the compute power to solve the problem. That was true for many years, but unfortunately, it's not true anymore. Yes, we can squeeze more transistors into a chip. No, it does not give us the performance we expect. And there are multiple reasons for that. I'd say the most important phenomena that we see is that we could increase the frequency when we could increase the transistor number. It wasn't just more transistors, it was more transistors running at higher frequency. That was true for years. I still remember when you went to buy a CPU, let's say an Intel CPU, you would look at the frequency to know how strong the CPU is. If it's 2 gigahertz, it's twice as fast as the 1 gigahertz CPU. So when you bought the marketing title was the frequency. If you look at today's CPUs, they run at the same frequency that a CPU could run 2 years ago, and even 5 years ago. The frequencies cannot be increased anymore. The main reason is power consumption. I'm not going to get in there, but frequencies cannot really be increased. It wasn't just the frequency. Adding transistors allowed better caches, allowed better technologies, and we had architecture advances from out of order execution, multiple pipes, all kinds of technologies that were implemented into CPUs to allow the increase in performance. Even there is slowdown. If you look at the newest technologies that went into CPUs, you'll find out that most of them are focusing on saving power, which is extremely important. I'm not going to say anything bad about it. The problem is that it does not allow us the growth in performance that we expect. And we want stronger and stronger processing engines. What happens due to that is that CPUs, we cannot build our compute machines, our compute power, all on CPUs. Unfortunately, we cannot just keep, waiting for the CPU vendor to come up with a new CPU so that we have more compute power. We need to go somewhere else. And going somewhere else means first, going into heterogeneous computing. If you look at today's data center, if you look at today's supercomputers, they are not all built on CPUs only. They are built on CPUs running with accelerators. Accelerators can be of the type of GPUs, and a GPU accelerates the computing. There is no GPU-only systems. The GPU systems will always have CPU nearby the GPU. I'll talk about that in a minute. But it's not always only the GPU. We can see Google, for example, building their TPU, the Tensor Processing Unit Cloud. Again, it's a CPU cloud which has TPU as accelerator that is accelerating tensor processing, mostly for AI. You can see more and more accelerators coming into the market, accelerating specific applications. And the reason for that is that CPU is an amazing machine. CPU on the same, technology, the same chip, you run your storage software, you run your operating system, you run your applications, you can browse the internet, you can play games, you can do whatever you want on the same CPU. Everything that runs on compute can run on a CPU. This is amazing. We got used to it, but I do believe it's an amazing technology that with single chip, you can do everything that you want. The problem is that this single chip that does everything with degraded efficiency. You cannot do everything in the highest efficiency possible. It's just like a Swiss Army knife, right? It has many functions, but none of those functions are the best in class. If you take the basic functionality of just cutting things with a Swiss Army knife, it's not like buying the best knife you can find, right? It's not as good as. Same for the CPU. CPU can do everything, but if what you want to do is, for example, tensor processing, matrix multiplications, CPUs is not very efficient at doing that. And if you only use CPUs, you will not get the performance that you need. This is where the accelerators come. An accelerator, if you buy a GPU cannot run your operating system, and it cannot run your storage in an efficient way. The GPU actually needs the CPU to be there to help with those tasks. The GPU can accelerate very specific tasks in a very efficient way. Same for TPU and same for other. So basically, if we try to look at where those technologies are going, you will see that you will have CPUs, and near the CPUs, you will have GPU, which is a programmable kind of accelerator, right? The GPU can do many applications, not everything, but can do AI and can do weather prediction and can do different applications. Most of them are focused on specific type of data processing, and it can do that in a very efficient way, but it's programmable. At the other end, you will see ASIC chips that were designed for very specific applications, like security, or chips that were designed to offload some specific security functionality. What happens is that CPU is the most flexible device that allows you to run whatever you want in not very efficient way. On the other hand, there is the specific ASIC, which does only specific application in a very efficient way. And eventually what you will see is supercomputers, which includes more than a single technology, right? Today's AI machines, most of them will have at least a CPU and a GPU, or a CPU and a TPU, right? If it's Google's processing engine. You will not see CPU-only machines doing AI training at scale. It's just not efficient enough. So this is where Moore's law plays a part. The second trend, right? I said I'm going to talk about multiple trends, unrelated. You're familiar with most of them, I assume. So the second trend is the exponential data growth. We generate data in a rate, in an unbelievable rate, right? Each and every one of us has a cell phone which generates data. You don't want to know how much data you generate with your cell phone. New cars generates tons of data. Everything is generating data. And data is a great opportunity. So first, a fact. 90% of world's data has been created only in the last 2 years. If you think about it, going back 2 years in time, you had 10% of the data that you have today. Or looking into the future is even more amazing. If you think about all the data that we have today, it's negligible compared to what we will have in 2 years. I actually had discussions with storage people at some national labs. I'm not going to provide names because I cannot, but I had discussions with the infrastructure people that are responsible for building new systems, new clusters, HPC clusters, and new storage islands, right, to hold all these huge amounts of data. And they said they are not deleting data, because it's a waste of time. Even if you take 50% of the data that you have today and delete it, 2 years from now, you save nothing. It's really negligible. So with generating so much data, it opens new opportunities. And looking at those opportunities, I'm just going to show what it means in terms of money. I know it's not the best way to measure, but it's an interesting point of view, and that is, sorry. And talking about money, the easiest way to measure is, the worth of companies. And I was looking at the 10 companies that worth the most, based on market cap, just looking at the stock market. And I looked at 3 different centuries. I should have probably a more updated soon. But if you look at 30 years ago, it used to be the companies were some technology companies like Microsoft, General Electric, Intel, IBM, selling computers, selling infrastructure. On top of that, we had energy companies, oil companies, and some pharmacy and medical devices companies. These were the companies that has the highest market cap. 10 years later, if you look at the list, it's very similar. We still have the energy and oil companies. We had some technologies companies. We had some pharmacy and medical devices companies. So the list was kind of the same, in the technology company, you can see mobile, AT&T and China Mobile getting into the list. But still, it's companies selling technology and hardware. And the funny thing is that if you look at the new list, right, the last decade, the companies that got to the top of the list are somewhat different, right? We still have one oil and gas company, which is interesting to see only one closing the list. That on top of that, we have some companies like Microsoft, which are sort of the old kind of technology companies. But we have a list of new type of companies like Amazon and Google and Tencent and Alibaba and Facebook. Those companies are different. If you look at the way they make money, they don't sell you a service. Usually, they give you a service for free, most of them. And the model they get money is by, once you use their services for free, they learn about you, they generate data, accurate data about you, us. It's not a specific person, right? It's about every one of us. They collect data, they process this data. Just collecting data is useless, right? If you just keep a lot of data on the disk, that's fine. It doesn't help you. What they do is process the data, learn more and more about every one of us, what we want to do, what we do, how we change our behavior, and they try to make money out of that. This is their model. This is their the way they make money, by selling us to their customers. They learn what we like. They get money from their customers to provide access to us based on what they understand and know that we like, that we do, that we need. And you will be surprised how much they know about us. So data is sort of the new oil and banking resource, right? Instead of selling oil, you can sell access to data that you mine in any way you choose, right? And probably the easiest way to mine data about us is by giving us services and following the way we use them. Google Maps is a great example. They know exactly where you are anytime, any. Facebook, very interesting to see. Specifically, research that was made on Facebook users with a large number, right? 86,000 Facebook users. It's a very interesting research looking at what Facebook servers can learn about the Facebook users based on the likes that they do, not on the data they share, only the likes that they mark on friends, posts on Facebook. What they did was to first analyze people's personality based on a well-known questionnaire that psychologists are using to learn what how people behave. If anyone is interested, I can share more about this questionnaire. And then they compared the results to what the Facebook computers and servers can learn about us. And they show that after 10 likes, after you only mark 10 likes, they know about you enough, just like your coworkers, the person who sits with you on the same floor and eats lunch with you. And after 70 likes, they know like your friends and roommates. After about 300 likes, Facebook computers knows you better than your spouses. I think it's amazing. I think that those computers can now know about us more than we understand ourselves. And they can know they can predict what we will buy, how we will elect, where we will go. They can predict everything that they do better than we understand how we behave. And with that, they can use that, to sell us stuff. They know what we will choose to buy, even if we don't understand that this is what we're going to choose to buy. So you can understand that, learning about us based on data is huge opportunity, and companies are doing exactly that. The next trend, right? We had two. We had Moore's law, and we had the availability and the importance of data. Next one is cloud computing. I'll do that very quickly. I think that it's very interesting to see that instead of companies buying small amount of computers to run their workloads, people use the cloud, which means that cloud companies are building hyperscale data centers with hundreds of thousands of processing engines. I'm not going to get into too many details. First, most of those details are not being shared. And second, I'll discuss why it's interesting a bit later today. And the last trend, obviously everyone understands that, and it's the most important application I think ever developed is artificial intelligence. There are many applications. I'm not going to get into applications. It allows you to build conversational systems where you can discuss, order pizza. The reason I have that here is that pizza is going to stay with us during this week, and I'll discuss pizza again in later. And it's very common today that you can order pizza or do other operations where you only speak to a machine that knows how to ask you the right questions, or I want to order pizza. Okay, what toppings do you want? How large it is? And build a conversation to fill in the complete questionnaire so that the machine now knows, the computer now knows exactly what you send you. Again, it's an example. I assume you are familiar with artificial intelligence, at least at some level. Some of you are more familiar, some are less. Just to make sure we speak the same language, artificial intelligence is a very hard to define. It's the quest of building a machine that can think like humans. I'm not really sure I can define what it means to think like a human or to act like a human. So I'm going to leave artificial intelligence aside, and our focus is going to be on machine learning. Machine learning is just a subset of artificial intelligence where you let the machine, the computer, learn how to solve a problem without building the algorithm for the machine. So it's a subset of artificial intelligence. And even that, when we talk about machine learning, there are multiple techniques of doing that. During this week, I'm going to focus on deep learning. Deep learning is the usage of neural network models to do machine learning. Again, when I say artificial intelligence or machine learning, during this week, I'm actually meaning deep learning. I'll try to use the deep learning term, but when I say AI, I mean deep learning. I'm not going to discuss the general topic of AI this week. First, it's a complicated one, and second, we need to focus. We're limited in time. So AI, short history. At least I like this history, so I'm going to make it very short. AI started many years ago. The idea of AI and using perceptrons and it's not a new technology. It started way in the past. And even backpropagation, which is the most common technique today for deep learning, is not new. It's a very old one. The problem was that, yes, the idea was well known in the past. The problem was that it wasn't useful. And for many years, people believed that there is no way to actually use those techniques beyond, writing some papers. So that was the AI winters, and only at some point it was reintroduced, and people started playing with the idea of deep learning. Again, I'm talking about AI with the focus on deep learning. And you know, people understood that, hey, maybe we can actually do something with that. And they actually started building systems that had quite a good success, from handwriting recognition and different ideas. And I'd say the main breakthrough happened around 2012. There were multiple parallel projects, from which I'm going to talk about AlexNet. I think it's the most amazing thing that happened in AI. A couple of students, Alex is one of them, he's not the only one. Well, forgot the name. Ilya, who is the CTO of OpenAI, was working with Alex. No one remembered that he was a part of that. What they did was to compete in the ImageNet competition. ImageNet competition was a competition where researchers that worked on picture recognition came with new algorithms to try and solve the image recognition problem and reduce the error rate of image recognition. Every year there was this competition. When I studied when I was a student, my main focus was image recognition. I learned the techniques. I was working on trying to build new techniques for image recognition based on old school algorithms. And what happened was that every year new researchers came with new algorithms or optimized algorithm, and you know, they could decrease the error with the system in, let's say, 0.1%. It was very slow progress with tons of efforts. Huge number of researchers around the world were working on that. And what happens is, this is, by the way, the competition. You can see 2010, 2011, and then 2012. You could see, you know, these are different participants. You can see the lowest error rate that could be achieved, and you can see that a year later it was a bit lower. And a year later, in 2012, there were still those researchers that came with the algorithms. It was a lot of fun, but then came AlexNet. AlexNet was the first time that someone came with an AI, deep learning-based image recognition machine. What happened was that Alex took the well-known backpropagation technique. You know, he didn't actually come with, well, he did come with some optimizations. What he did was to convert the AI backpropagation to run on a GPU, so that it was easier and faster, and you could build a large neural network. Well, large, we will talk about what large means, but a larger neural network to enable more accurate image recognition. And you could use the ImageNet database, which included, I think, about 20 million pictures. I don't really remember. Don't take me on that one. And he came with a neural network, and you could see that the progress he did in 1 year, moving from the common state-of-the-art algorithms, moving to deep learning, was amazing. It would have taken the researchers 20 years to get there. And what happened is that from that point, all the old school, the algorithmic work on image recognition just didn't make sense anymore. And everyone moved to deep learning based algorithms. And, you know, everything that I have learned in the university and all the research hours that I spent on the traditional image recognition techniques is useless. It was replaced by a machine that learns how to do image recognition based on deep learning and neural networks. What happened was that before that, everyone knew how to, or the research researchers knew how deep learning should work, knew what a neural network should look like. The only problem was that you actually didn't have enough compute power to train a large neural network with a large amount of data. It wasn't feasible to use that. What happened in 2012 is that people, including Alex and Ilya and the rest of the team, understood that a GPU could do that way more efficient than a CPU, and they became, I wouldn't say the first, it's hard to say that, but it was a breakthrough saying, hey, we can now train neural network. We can now train large neural network. It's not limited to just 2 or 3 layers of neural network. We can build deeper neural network. And we can train that with a huge amount of data on a GPU in a reasonable time and change the world. We don't do traditional image recognition anymore. It doesn't make sense. And that was 2012. You know, it was more than 10 years ago. There has been huge advancement in what neural networks can do. I'll try to discuss that a bit later today. So again, why now, or what happened that changed the world from doing algorithms for different problems, moving to AI? It's mostly the compute power. The other approaches could get better accuracy with less compute power. But once you have the compute power, once you have more compute power, neural networks gives way more efficient recognition or way more efficient techniques compared to the other approaches. And today we're somewhere here, right? We're solving problems we couldn't even start solving before. I don't think anyone could have self-driving car based on standard approaches without deep learning. I don't think anyone could even dream of building a machine like the ChatGPT or the other language recognition or language models without deep learning. We weren't even close. We couldn't even dream about solving these kind of problems. Today, we're trying to solve problems no one thought are possible to solve. And the interesting part is that I'm quite sure that in 5 years from today, we will be solving problems that we don't dream about today. The advancement was huge. A few words about neural networks. The idea was to take a neuron, right, part of our brain, see how our brain works, and build a mathematical model of a neuron. I'm not going to get into details, but the idea was to try and emulate the way our brain works. By the way, our brain works just like neural networks that we use today, or very much like that. And an important part that I've just learned recently, the only time that our brain really learns into the long-term memory is when we sleep. So I'd recommend that during this week, use the nighttime for sleeping, not just for learning. Otherwise, the learning is not efficient enough. Now, going back to our topic, so this is a neuron, it has its different part. The idea is that it has the part that does the actual mathematical parts. It has sensors that connect to different neurons and gets input from different neurons. And it gets the outputs, the axon terminals that sends notifications, sends some data to other neurons. So each neuron is connected, collecting data from a bunch of neurons and transmitting data to a bunch of neurons. This is the brain, and this is exactly an artificial neural network. And again, I'm going to skip the details. So artificial neural networks build out of neurons that have inputs coming from other neurons and outputs going to other neurons. And we build layers on top of layers. And I said that, you know, all the traditional way of doing picture recognition, for example, was kind of a waste of time. And now people are doing deep learning. It's not very accurate. Deep learning is actually employing some techniques that were inherited from the old way, from the traditional way, like doing convolutions on pictures, on areas in the pictures, doing different things that came from the traditional image recognition. But again, it's different. It's a new kind of technique to learn how to do image recognition. And again, we said we are generating more data, right? So we use deep learning to process this data and become a more accurate technique for learning whatever you want to solve. And maybe again, I'm going into the past. We talked about AlexNet, right? In 2012, the first AI-based algorithm for image recognition competing in the ImageNet competition. Obviously, you know, it was the first neural network, and then came GoogleNet and ResNet and Inception v4. What I'm trying to show here is the size of these colorful marks are actually showing the complexity, the amount of compute resources needed for training the neural network. So if you only look at AlexNet compared to, say, Inception v4, in 4 years, the compute requirements grew up 350 times. Obviously, even if Moore's law was still alive, you couldn't do a CPU that is 350 times more has more compute power compared in 4 years. You cannot even dream of doing that. And without Moore's law, it's just impossible. I have another example of speech recognition. Again, in 3 years, going 30 times, it's not as high as 350 times, but again, it's 30x. We are not able to generate a new processing engine that provides this speed of growth. It's not enough to just buy the new CPU or GPU or TPU. It will not be 350 times stronger than the one you could buy 4 years ago. It will be stronger. It will have more capabilities, but not at the area of 350 times. Okay, so let me try and take everything into one picture. We talked about Moore's law, so CPUs cannot cannot grow in performance at the rate that we want, right? They don't even grow 2 times every 24 months. We talked about the amount of data that we generate. We talked about AI processing the huge amount of data. We shortly talked about those huge data centers that cloud computer are building. And I want to gather everything together and say, okay, so looking forward, we need a supercomputer, or we need a computer that will give us better weather prediction, right? Or a supercomputer that will be able to do crash simulations for car manufacturing, or we want to build a supercomputer that can faster find a cure for a disease like we had with COVID-19. And we need supercomputers to just run and train huge neural network models to do whatever you believe you would like to do with that. And that can be self-driving cars, ChatGPT-like, and other generative AIs that allows you to build pictures, create music, create movies, and whatever you can dream of today or will dream of in the coming future. We cannot just build a server that will do that for us. It's obvious it's not going to happen. And this is where I wanted to collect, the past and connect it to the future. And the main answer for that is, hey, we have way more data. We're building larger and larger AI models. we will need to connect GPUs and CPUs and ASIC accelerators and FPGAs and storage and whatever you can believe you need to connect. And we need to connect that in an efficient way. It's not enough to just put everything together, and connect it to some legacy network. It's not going to be efficient enough. If you buy the fastest GPUs, but they spend half of the time waiting for data to process, it means that you don't get the compute power that you want. If it's also true for CPUs, ASIC, and now we have a very complicated system with different processing engines and different accelerators and different kind of storage connected. And we need faster interconnect. And by the way, it's not just faster interconnect. And what I am going to try and convince you today is that faster interconnect is important, but fast is not good enough. And this is where in-network computing, this is where other technologies come into process to allow us to connect all those CPUs, all those GPUs, all the ASICs, everything together into a single strong machine. It's not just a collection of processing engines. Eventually, what you will look into, the data center that you build with all these processing engines and storage and everything, it is the computer. It's one computer that runs an application that tries to train a neural network, tries to predict the weather, or tries to solve any other problem. It's a single computer. And we need to keep looking at it as a single computer. From now on, the data center is the computer. First a CPU was a computer. Today, if you buy a server, dual socket CPU, it has two CPUs. You don't look at it as two computers. It's a computer built out of dual socket CPU, right? Dual CPU socket. For me, a data center, which includes tens of thousands, maybe even hundreds of thousands, CPU sockets or GPUs or any other processing engine, or even a combination of tens of thousands of CPUs and tens of thousands of GPUs plus ASICs, everything together. For me, it's a single computer that is designed to solve tomorrow's problem. And this is what we are going to focus on in this coming week. What is needed to allow the scale and the performance and the efficiency of the supercomputers of the tomorrow? Now, we've already talked about in-network computing. I think it's time, maybe before we go deeper in there, let's take a 10 minutes break, actually 12 minutes break. Let's meet together at 4 p.m. where we will go into more details about what it means to do in-network computing. And I'm going to take this time and look at the chat and see if there are new questions. Again, if you have more questions, please write in the chat, or you can unmute yourself and interrupt me. I'm very much okay with that. See you all at 4.
Order coffee or coffee for Kiba.
Okay, so I'm back. Hope you're too. Before I continue with the slides, we have two questions now. Let's start with the last question about comparing GPU and DPU for matrix multiplication. So the easy answer, the short answer is, if you need to multiply matrices, go to the GPU. GPU is designed to do that in a very efficient way. Again, I'm not going to dive into the details why GPU can do that better than CPU, but GPU was designed to do exactly that. The DPU, although it's called data processing unit, the idea behind DPU is to process data that has to travel through the network anyway. It's not used as a local accelerator that accesses the memory and just do data crunching. It's very good at, the DPU is very good at processing data that goes from one server to another. It has to go through the network anyway. So on the way to the network, you can do all kinds of smart things with the DPU. And later this week, we will have multiple examples to where DPU really shine and excel. Specifically data processing, matrix multiplication is done on the GPU. The other question about non-contiguous data, again, I did not forget that, and I promised to get there before the end of today's presentation. So we went through all kinds of trends that shows that, hey, we're having a real problem building a system, a machine that can provide the computation power that is needed and the throughput that is needed to actually solve the problems that we are trying to solve. We were looking into what happened in about 10 years ago at ImageNet, AlexNet, and how image recognition neural networks require more and more compute power. These days, it's different numbers. If you look at GPT-3, for example, it has 175 billion parameters. We haven't go through in details what a parameter means. So if you're familiar with AI and deep learning, that's great. If not, just to give you a very high-level view, what happens in a neural network is that you have many neurons, and you have the connectivity between the neurons. Each neuron has the output that goes as an input to multiple other neurons. When we learn, when we optimize the neural network for a specific task, what happens is that we change the weight of each one of those connectivities, right? Each input to a neuron that comes from a different neuron has a weight to the input that says, how important is this input in the calculation of the output of the specific neuron? By the way, this is exactly what happens in our brain. What happens is that the neurons are not moving. We don't grow new neurons. What happens is that the connectivity between the neurons is changing. A neuron that connects to another neuron that has no effect, no real effect on the output, the connectivity will just degrade to the point that it might even disappear, and connectivity to other neurons might be stronger. This is how the brain is learning, and this is how artificial neural networks are learning. So we have those weights, the importance of each connection, and we try to tune all the weights. This is the only thing that changes in an artificial neural network. We try to tune the weights in a way that eventually will give us the best performance of the neural network. So the more parameters we have, the more things we need to calculate and change at each iteration to eventually have a good and accurate neural network. So it used to be in the order of thousands, and then tens of thousands, and hundreds of thousands, and millions. And today we're talking about hundreds of billions of weights of parameters to a single neural network. And when we talk about database that we use to train, we talk about huge databases, eventually it requires a huge amount of compute power. We don't have a CPU or a GPU or whatever processing unit you can think of that can do all of that in a reasonable time, right? You don't want to start processing and have the results in 1,000 years from today. It means that we need to connect a large amount of processing engine, and the huge connectivity and the efficiency that is required is so high that this is the challenge we're going to try to solve. And we talked about CPU-centric or traditional data centers where everything, all the computation happened in the processing engines. And we already said, or at least I said, I do hope you actually believed in what I said, or I can convince you during this week. We need to move some functionality into the network. And the reason is that it's more efficient. It's not that, networking engineers are smarter than CPU or GPU engineers, and they know how to do math better than a CPU engineer. That's not the case. Building, an ALU, arithmetic logical unit that does, floating point calculations, everyone can do that. It's not that complicated. Building a CPU is way more complicated. Building a GPU is way more complicated. But, just processing data, building a chip that processes data is not that hard. It's not that networking people know things that CPU people don't. It's the difference on where you solve the problem. It changes the complexity of solving the problem. And I'm going to show you a very quick example for that. And I said we're going to talk about pizza again. So here's my pizza example. Let's talk about ordering pizza. I want pizza. I'm not going to make my own pizza. Multiple reasons. One of them is that currently I'm not at home, and I don't have access to whatever is needed to make pizza. So I'm going to order pizza. And the flow is quite simple, right? We all know how to do that. I call the pizza place or use some pizza application. I might even talk to an AI machine, but that's not important. What's going to happen is that someone will start preparing the pizza, taking the dough, putting tomato sauce, cheese, pepperoni, whatever you like on your pizza, as long as it's not ananas, I'm fine with that. Pineapple, sorry. And with that, once the pizza dough and everything is on top, you put that into the oven, and now you wait, right? You wait in the oven. It's usually a couple of minutes, 5-10 minutes, it depends on the oven. When that's done, you pack and send it, and now again it will take 10 minutes if the pizza place is not too far, and then you get your pizza. I would like to introduce you a new technology, right, for pizza. Think about it. What if we had a truck that had the pizza oven? So what we could do is actually take these two steps, right? The pizza is in the oven, and the pizza is being delivered. Each one of them is about 10 minutes, but if you overlap them, if you put the pizza in the oven and put it out for delivery at the same time, you actually save time. You save 10 minutes. On top of that, you will get the pizza warmer, which is extremely important, but not related to networking. If you could bake the pizza while delivering it to the destination, it would be way more efficient. This is actually why I'm saying that, hey, you have to cross the network. it gives you opportunities of doing things and processing the data while you cross the network. It changes the way you solve the problem. It's not just, you know, a new pizza truck. And again, I'm going to show the example we already talked about earlier for doing in-network reductions. Reduction is an extremely important operation in distributed computing. Many applications are using reductions. You know, it's a very simple technique to have a large problem, break it into smaller problem, solve the local problem on each processing engine, and now, hey, you have a bunch of local results and you need one global result. This is the reduction operation. So distributed computing, many applications, not all of them. There are other techniques to do this distributed computing, but many applications are using that. And maybe the one most important application is using data reductions, and that is distributed deep learning training. This is not the only technology that can run in the network. There are many technologies and many acceleration engines. There was a question specifically today on non-contiguous data access, and I'll discuss that today. We talked about the system, which is a bit more complicated today because it's not just one processing engine. We have the CPU and we have a GPU, and we might have other accelerators. So everything is a bit more complicated, and optimizing that is using many of the what I would call extended in-network technologies. It's not just computing, but data access. There are many things we need to build into the system to have the network that allows you to connect everything into a single computer. So let's maybe go back one step, and I'd like to say, I started with, hey, we need faster network, and I told you that I think faster is not enough. It's not what we need smarter or more efficient network, and it's very hard to say what it means, smart network. Hey, it's not going to make coffee, so it's not going to make pizza. What does it mean, a smart network? We will discuss that. So taking two steps back, we still need low latency. It's not that we don't care about fast networks. If you could have zero latency and unlimited bandwidth, I take that, and I'm not going to ask for anything else but that. But we cannot, right? If you look at the latency of interconnects, looking back, I don't know, about 20 years ago, it used to be latencies in the ballpark of milliseconds. It used to be protocols like socket, TCP, that requires OS software intervention that caused, you know, context switch. Latencies used to be in the ballpark of milliseconds. And then came RDMA and user-level networking and other technologies, and the latencies were reduced to the ballpark of today's microsecond latency, point-to-point. And if you look at this latency, I don't expect to have nanosecond latency in 10 years. The reason is that we're getting to the physical limits. The time it takes the light to go through an optical cable cannot be accelerated. Unfortunately, at least I don't know of a way to go beyond the speed of light. Meaning, if you have a cable with the length of 100 meters, it takes the light time to get from one end to the other, and we cannot accelerate that. So latencies, we sort of got to the lowest latency we will be able to withhold. I don't think you will see lower latencies. The other part is bandwidth. We need high bandwidth. I'll come back to that one later. We need high bandwidth. This is an old slide that I stole from someone. I was too lazy to make my own. It comes from Sylvain from NVIDIA. who presented that in a GPU communication, GPU conference. I'm not going to sell any GPU here, but the idea here is that it is showing the communication scheme and the communication bandwidth required within the system and between systems. And it's showing that, hey, we are building fast links in the system between GPUs. There is a dedicated bus connecting the GPUs. And within the GPU, we have the internal network that has its own bandwidth. And if we don't match that with the node-to-node bandwidth, with the network, the interconnect bandwidth, we will not get the bandwidth that we need. Maybe a different way to do that. It's an old test that we ran on 100 gigabit per second. You know, now we are talking about 400 gigabit per second, but it was comparing 10 gigabit per second, 25 gigabit per second, and 100 gigabit per second on TensorFlow training, multiple GPU, 32 GPUs. What it shows is that with exactly the same technology, it's the same network adapter, just limiting the bandwidth, we show that more bandwidth provides you faster training. It provides you better performance. So again, fast interconnect is extremely important. We need low latency and we need high bandwidth. I'm not trying to say it's not important. What I'm trying to say is it's not enough. And beyond that, again, this week is going to discuss RDMA in depth. So we compared RDMA to the competitor or the traditional technique. You know, probably each and every one of you had some opportunity to implement some server client code or some communication code on top of sockets, TCP sockets. This is this still is the most common way and technique to communicate. And in most cases, I'd say go TCP socket. If you want performance, it's just not good enough. And we will discuss in depth why it's not good enough, but it's not good enough. So what we did is compare RDMA to TCP socket. First, as technologies, let me go through the differences in technologies in high level. Again, we will discuss that again during this week. The main features of RDMA are first, it's, you know, the RDMA, I can access remote memory directly without the need for the remote CPU to be involved in that, unlike TCP/IP or unlike socket. One side needs to send the data, the other side needs to receive the data, and the data will be copied to the receiver buffer. In RDMA, the receiver is not involved in or does not have to be involved in the delivery of the data. I can put data in a remote server's memory directly without any intervention of the remote CPU. This is the first benefit of RDMA. It's not the only. It's still, RDMA does support the send-receive type where one sends and the other receives data, but it also implements this read-write. Just put data in remote processing engine's memory. The second one, and probably the most important one, is the kernel bypass. If you look at TCP/IP, your operating system implements the socket APIs, and underneath the socket APIs, it implements TCP protocol with IP protocol and the Ethernet drivers. There is a bunch of software running for allowing you to send and receive data that is implemented as a part of your operating system kernel. Meaning every time that you write to a socket or read from a socket, you actually call a kernel code, a kernel module. So you do context switch, which is very expensive for the CPU, for each send and receive of data. RDMA, unlike TCP socket, has a kernel bypass, which allows the user level to directly communicate with the network adapter and send and receive data without going through the kernel. So the network adapter needs to implement everything that the kernel used to implement. That includes multiplexing and demultiplexing data from multiple processes, right? You can have more than one process sending and receiving data. So instead of the operating system that does the multiplexing and demultiplexing for you on top of your sockets, now it's the network adapter hardware. It needs to build packets. It needs to implement reliability protocol. All of those are offloaded into the network adapter hardware so that the user level software can send data directly from the user level buffer through the network adapter to a remote memory address in a remote server. Again, unlike TCP socket, where the application will call the socket software, which is a context switch, and the buffer needs to be copied to a socket buffer. And then there is the TCP protocol transport implementation. Again, it's another data copy, and then you need to call the NIC driver, and you might have another copy, and everything is in the kernel. So we had a context switch. Data is being sent and received in the other side, and you have exactly the same, right? When crossing the data that arrives needs to go through the TCP code and then the socket code, and you copy the data, and eventually you receive it at the application buffer. When we talk about RDMA, the user level application can communicate directly through RDMA NIC, a network adapter that supports RDMA. The buffer is not copied. You don't call the kernel code. You just bypass everything, go directly to the NIC hardware. Well, it's going the other direction, sorry. So again, you copy the data directly to the NIC hardware, which sends it and receive. So it's way more efficient. You don't have data copies, no kernel code, less software, which for the application provides you lowest latencies, higher bandwidths, lowest CPU consumption, right? The CPU doesn't have to do transport and socket, and so it frees up the CPU to actually do what you want the CPU to do instead of doing networking. And eventually it provides you higher performance. And this higher performance, we talk about bandwidth and latency. What we care about is application performance. So again, in a small experiment, we measured ResNet 50. It's a neural network used for image recognition. And we measured with the same GPUs, same system, same network adapter. All we changed was RDMA versus TCP. And we were trying to measure the efficiency of the training application on top of a system with, I think, again, 32 GPUs. Yes, 32 GPUs. And let's just look at the graph. Forget about the numbers. Let's look at the graph. What you see here, the highest line, is the theoretical performance you can achieve. What it means is that if one GPU has X performance, the theoretical speedup you can get with 32 GPUs is 32 times the performance of a single GPU, right? You cannot expect to buy 2 GPUs and have more than twice the performance of a single GPU. So this is the theoretical 100% efficiency. You cannot get beyond that. And what we compared is same training on those GPUs, once with RDMA and once with TCP. And you can see that I'm only looking at the numbers with 32 GPUs. X-axis is number of GPUs. This is the speedup. And we can see that if you use TCP and buy 32 performance, you get about 20 times faster than a single GPU. You paid for 32 GPUs and you get performance of about 20 GPUs, 20 times faster than a single GPU. If you do RDMA, you can see that it's about 31 GPUs, 31x. It's not 100% efficient. there is inherent overhead of taking a problem and distribute it to multiple GPUs. We already discussed that you have some communication that you didn't need if you only used one GPU. So you can never get to 100%, but hey, we bought you about 10 more GPUs, 11 GPUs, performance-wise, for the same money of GPUs, for the same amount of GPUs, for the same power. So RDMA, it's the same bandwidth. It's the same, the same network bandwidth, right? We use the same switches, the same cables, the same network adapters, the same everything, except different protocol, different transport. And we see it has huge effect on performance. This is a part of why I said, hey, it's not just fast network. It's not just, hey, I need 200 gig, or I need 400 gig of bandwidth, or I need 800 gig. It's how you use the bandwidth. And RDMA is an important part of that, and we will focus more on RDMA during the coming week. But again, it's not enough. We said that, hey, I'm not going to do training on a CPU. CPU has issues with prefetching data for matrix multiplications and has very low efficiency. So we need a GPU. And now if you look, I don't know, 10, 15 years ago, when you have a system, I'm sorry about that. When you have a system with a CPU and a GPU, basically the old way to do communication, right, is that the CPU owns the network adapter, the CPU owns the network, and if you want to process data on the GPU, that's fine. You can copy data from the CPU memory to the GPU memory, process the data, copy it back to the CPU memory, and now the CPU can do communication to another node that could later copy it back to its own GPU and do the processing. With the introduction of GPU Direct RDMA technology, the idea is that now the GPU, even though it's not the owner of the network adapter, right? If you look at PCI topologies, and again, this is way beyond what we're going to talk about this week, there is one root complex, one owner of the PCI devices, and that's the CPU. But still, we want the GPU to be able to communicate without going through the CPU, because all those copies adds overheads and reduces the performance. So with GPU Direct, you can let the GPU, it can definitely be any other accelerator, right? If you have a different accelerator, you would want this accelerator to have this accelerator direct or GPU direct or whatever you want to call it, so that a device that is not a CPU can use the network without going through the CPU. So GPU direct is important. Again, I'm not going to discuss the performance number. And the last and most important technology that I'm going to introduce in details now, or in more details, is the in-network computing, Sharp. And we already discussed a system with multiple servers connected through switches and cables. And we run distributed application. Each host has its own part of the problem. And now we want you to calculate the average of the result each host has. Let's say that it's doing deep learning, data parallelism. Again, I think that we're not going to dive into data parallelism today. We will do that later this week. But in data parallelism, what happens is that each GPU or each processing engine has its own model and try to do training on its own part of the data. And eventually each server, each processing engine has a very long vector of parameters that that are used to fix the neural network, to change it calculates the gradients to fix the weights or the parameters of the neural network. And before we can actually update the neural network, we need to calculate the average of those vectors. So each host has a long vector of gradients, and we need to somehow calculate the average of all those vectors, and each host needs the result of this average This is exactly the all reduce that we talked about earlier. And we talked about what happens if you do that in software. You need to do that in pairs and then between pairs and more iterations until you cover everything. It's a multi-iteration, very long and very expensive operation. But here's the deal. You take the switches and implement some processing engine within the switch so that when data arrives from all the hosts to the switches, right? If it's a very small drawing, so I only have 5 hosts, think about 50,000 hosts. Probably you will have multiple switches, right? At the leaf layer, you will have those switches and you might have more layers of switches, but the topology is going to be looking like a tree for us. So what happens now is that each leaf switch gets the data from the hosts connected to the leaf switch and actually calculate the average. The interesting thing about switch is that switches are designed to get data from a large number of sources, right? Here we only have a small number of sources, but think about a switch with, I don't know, 64, 128, 256 ports, meaning you have many connected GPUs to a single switch. And the switch is capable of absorbing data at very high bandwidths for from a large number of sources. So the switch has the opportunity now to calculate the average from all its inputs at the same time and send the results, again, to the next layer of switches. In this case, it's the root of the tree. If you have hundreds of thousands of GPUs, you'll probably need a third layer of switching. So you would have seen, more switches in the second layer, and then one switch at the third layer, the root. And now this root actually has the result of the data aggregation, has the result of the averaging of all the input vectors. Well, all it has to do now is sending back the result, the aggregated results, to the hosts. And you do that, and you actually solved the averaging of the different vectors. So you actually have 2 benefits. One is the complexity is lower. You don't need multiple iterations of sending and receiving data. You send the data once, and you receive the result once. There is also a second very interesting benefit to that work, and that is the average calculations actually happened in the network. And the GPUs, they are not occupied by sending and receiving data because they use RDMA, and we said that with RDMA, you don't have all the software involved in sending and receiving data. The NIC does that for you. And the averaging is happening in the switches. So with the combination of NICs and switches, actually, when you do this reduction, when you do this averaging of your vectors, the GPUs are not involved. What happens is that at that time, the GPUs can actually do real work. Going to neural network, for example, you can start with a few layers of your neural network, calculate the gradients, calculate whatever you want, and start the data aggregation, start the averaging of those layers. And while the network is doing the averaging for you, the GPU can actually focus on calculating the next layers. So yes, when we distributed the problem, we added this extra overhead of calculating the averages of those calculations. But here we can actually hide this extra overhead while the GPUs are busy calculating gradients going through the next layers of neural network. I'd say we understand that networking cannot be zero latency and cannot be infinite bandwidth. But if we could hide the networking work behind processing, right, doing this kind of pipelining, that while GPU is processing, the network does everything that is needed for networking. You could actually keep the GPUs processing all the time and get closer to 100% efficiency. So instead of having infinite bandwidth and zero latency, we try to overlap. We try to let the network focus on networking. And networking is not just moving data from one point to another. For me, all reduce, right? The operation of averaging between multiple GPUs, averaging the vectors, is actually a networking problem because it connects a large amount of GPUs and does some operation between those GPUs. Think about it. The network is responsible for all reduce. GPUs are responsible for matrix multiplication, backpropagation, forward and backpropagation and all that. And they work in parallel. And if you tune that in the right way, if you implement that in the right way, this in-network computing allows the GPU to focus on what you want him to do and have close to 100% efficiency. So it's not just that we changed, from log n kind of algorithm with expensive algorithm, sending and receiving data at the same time. We also separated the work in a way that the network is responsible for this work, freeing up the GPUs to do different things. Great scaling, great efficiency when you do that in the right way. This is why I was trying to say that, hey, if you give me zero latency and infinite bandwidth, I wouldn't talk about in-network computing. Since it's not possible physically, we cannot move infinite amount of data in zero time. The best way now to make an efficient system is to try and overlap, try and make sure that you don't wait for data on your GPUs. And to do that, you need asynchronous offload of this complex communication scheme, right? It's not just moving data. We talked about calculating average and sending the results to everyone. It's a broadcast kind of operation. So we took a complex operation, offloaded it into the network, and allowed the GPUs to focus on different things. Obviously, it has very interesting performance characteristics. I'll start with the basic, right? How much time it takes all reduce to happen. We talked about the software algorithms that are in the order of log the number of nodes, log the number of participants. We compare here the dashed line are software implementations, the solid line are in-network computing hardware implementation. It's kind of a small scale just because I don't have a large cluster, no good reason. And what you can see here is that, yes, software implementation, and by the way, I didn't take bad software implementation. What we are showing here is our software implementation. Software implementation I've been involved in for many years, best-in-class software implementation, but still, the more GPUs you have, the longer it takes to calculate the average. Compared to in-network computing that have flat latency, right? It's different messages size, but you can still see flat latency, meaning the larger your system is, the larger the benefit of this in-network technology, because I'm giving you the same latency regardless the number of GPUs. If you're still in focus, I'm hoping I'm not too boring, you would see that, hey, I'm somewhat cheating, right? It's not flat latency. There is this jump between 8 GPUs to 16 GPUs, right? It's not staying flat. Other than that, it shouldn't change. This jump is because what we did in this experiment is to build, to connect 16 nodes per switch. So, or 8 nodes per switch. So what happens is that up to 8 nodes, you only need a single switch layer. Going beyond 8 nodes, you actually have 2 layers of FATRI. Okay, FATRI is not that interesting, the fact that it's FATRI, because we build this aggregation tree, which has only a single root. We don't need more than that. But the idea here is that we have this system up to 8 nodes. It's a single switch hop, flat latency. Beyond single switch hop, you have 2 switch hops, which gets you to a bit higher latency. I don't remember, it should be less than a microsecond difference. And then it stays flat, and with 2 layers, you can connect thousands of GPUs. And if you want tens of thousands or hundreds of thousands GPUs, you'll actually need 3 layers. So hey, you will see yet another jump, or yet another delta in performance, meaning you pay another half microsecond, ballpark. I don't remember the exact numbers. So again, it's negligible compared to the log n growing latencies of doing all reduce. Okay, so I thought I have more slides here. So let me now go back and try to answer the previous question. And before I do that, I want to discuss more things. You know, in network aggregation is probably the easiest technology to explain as an in-network computing. It's by far not the only one. It's very nice because it changes everything. It changes the algorithm, it changes the complexity, and it changes the location you do things. But there are many others. One great example is the question that we had here before in the previous hour that I said I'll answer now, talking about what happens if the data that I'd like to send is not contiguous in the memory. And hey, that happens. It's extremely common. It's actually so common that in some cases there is no way to avoid that. Let's say that you have a large matrix sitting in your memory. If you look at the memory, you know you don't have a matrix in the memory. You have contiguous memory, meaning either you start with the first row and then the second row and then the third row, or you start with the first column and then the second column. It has to be translated from 2 dimensions to a single dimension because your memory is single dimension. And now, no matter how you choose to do that, if you choose to do that by rows or columns, if you choose to do that by columns and you want to send a row, it will be non-contiguous data. Each cell sits in a different location in your memory. If you choose to do that in columns, your rows will not be contiguous. And unfortunately, many applications require that you send both rows and columns. So one of them will never be contiguous data. So how do I do that? The answer is, if you look at your software, what happens is that when you ask to send non-contiguous data, your software will go and collect this data and copy it into a contiguous buffer and then send it. And hey, this is not the most efficient way to send data. If every byte that you want to send, you need to copy first, you waste CPU cycles, you waste memory bandwidth. Hey, I want the data to be sent to the network while the GPU is processing the data, meaning there is a lot of stress on the memory. So adding to that yet another copy means that, hey, your memory bandwidth might become the bottleneck. It adds latencies. There are many reasons why you don't want to copy data. It's not an efficient way to send data. I want to send data from where it resides. And there are multiple solutions for that. We've been promoting, well, I've been working on multiple technologies that can resolve that. One of them can be just use a DPU, right? We said, what is a DPU? A DPU is an additional processing engines, additional CPU, flexible programmable CPUs with their memory subsystem that are separated from your main processing engine, CPU, GPU, whatever it is. And it's integrated with the network. So you could always say, okay, I'll do software that collects the data and send it to the network. I just run it on the DPU so that now I don't waste extra bandwidth on the GPU memory subsystem. I don't run extra code on the GPU. I just move it to the DPU. The DPU is responsible for all the data movement. So this is a part of the data movement. I can have the DPU, when the GPU would like to send non-contiguous data, it will tell the DPU, hey, I need to send this data, please send it on my behalf. The DPU has ways to send data directly from your application memory, and it can be a GPU or a CPU memory. It doesn't need to copy that into its own memory. There are techniques to do that. I might be able, if we have time, we will discuss that, how it's being done. So you might offload that to a DPU or any programmable engine you have in your SmartNIC. That's one way. There is another technique which utilizes the way RDMA adapters send data. We said that RDMA adapters can access your user memory directly. It means that your RDMA network interface card actually has some kind of access to the virtual memory to physical memory translation tables. Again, I don't want to get in too many details, but there are ways to build the translation tables that shows non-contiguous data as virtually contiguous data. And then once you work on top of this virtual contiguous data layer, you actually send contiguous data. The network adapter now gather the data from the non-contiguous physical memory, but it looks just like a virtual contiguous memory. So there are multiple techniques. They are all a part of, in-network computing or in-network acceleration. Again, the worst thing to do is having your processing engine copy data. It's not what you want your processing engine to do. You want everything that relates to the network to go into the network and be executed by your network interface card or to be executed by your DPU, the SmartNIC, whatever kind of interface card that you have. You want the interface card to do this kind of processing. And so this is a second kind of in-network computing, and that is just access to non-contiguous memory. And I'd like to just briefly talk about a third technology that I'll discuss in more details in Wednesday, and that is all-to-all communication. I'll try to do that in let's say 5 minutes. And again, I promise to get the details on Wednesday. When you do all-to-all communication, we look at two different ways to do that. Let me stop sharing the presentation. It will be easier for me. So when we talk about all-to-all communication, basically, there are two cases. If first, all-to-all means that I need to send to all the other participants in the group, and everyone needs to send to all the other participants different data to each participant. It's not a kind of a broadcast because I send different data to each participant. So when I send long vectors, when I send a lot of data to each one, the main problem will be bandwidth, right? I have a stress on the network. Everyone is sending to everyone. I have incast problems, and I have network utilization problems. And optimizing that is one kind of a problem that I'm going to ignore for now. Another one is the case of sending very short data to each one, meaning that, hey, I'm going to generate, let's say, let's imagine a system, right? It's not an AI system for now. Let's start with traditional high-performance computing systems with CPUs. Let's try to make it easy. Let's say that I have 1,000 servers. Each server is dual socket Intel CPU, and let's say that each CPU has 50 cores. So a server dual socket is 100 cores. So in total, I have 1,000 cores per server, 1,000 servers. It's 100,000 cores on a not very big cluster. And let's say that now I want to run an application, a distributed HPC application. The most common practice is to run a single process or a single rank in MPI terminology on each one of the CPU cores. So I have 100,000 processes, meaning each process needs to send 100,000 minus one. Let's stay with 100,000 different messages in an all-to-all communication pattern. But let's, instead of looking at the process, let's for a second look at the network adapter that you bought and put into the server. So this network adapter should allow each process to send 100,000 messages, but this single network adapter actually serves 100 processes. We said we had 100 processes per server. So the number of messages that a single network adapter needs to send for a small all-to-all operation in this small cluster is 100 times 100,000 messages, right? So it's if you want to do the math, it's actually number of processes per node square, right? Times number of servers. It's a huge amount of messages. It's 10 million messages for a very small operation, very small all-to-all operation. Meaning in this case, again, we will probably discuss more the performance model and the performance bottlenecks. Generating a message has some cost. It's not just sending 8 bytes. Let's say we do all-to-all of 8 bytes. It's not just the 8 bytes sending on the wire. You need to generate the message. You need to generate notification that it was completed. It requires work. So for small messages, if you look at all the network adapters in the market, they have some limitations. They don't really send small messages at full wire speed. And now we need to send 10 million messages from one network adapters to all the others. The performance is not going to be very good, no matter what we do. So if you look at the state of the art, there are some implementations like the Brook algorithm designed by Brook, that instead of just sending messages, so I need to send 100,000 messages, one to each peer, I will send a message to one peer that includes not only his data, but also data to other peers, so he can later forward it. And this way, I don't need to communicate with everyone, but what happens is that data goes through the network more than once. Data that needs to go to one destination will go to a different process first and then to another process. What it does is actually trade off. It trades off the message rate. Sorry, it trades off the bandwidth because I waste bandwidth. If I send the same message more than one through the network, I actually waste bandwidth. It trades off bandwidth with message rate. Now I need to send less messages, but I waste bandwidth. What I'm going to show you is that with smart in-network computing, there are other ways you could do that. First thing you could do is I want to send all the data that goes from node A to node B in a single message. I don't really want to send so many messages. You know, each process here sends data to each process here. It's 100 squared messages. It's tons of messages. I want to send a single message. But I want this message to include data from multiple processes, and I want it to include data to multiple processes. You could definitely do that in software, but then it requires communication between the processes on one node, communication between the processes on another node, data copies, plenty of inefficiencies. You could easily, or you could implement that into your SmartNIC. Let your SmartNIC do that for you. You could do that with a DPU, with software that collects the data from the different processes, send it to a remote DPU that will take the long message and split the data to the different processes. You could easily build an algorithm that doesn't send small messages because they're inefficient, send small amount of messages. So it reduces all the overheads of building messages and has zero copy, no data copy in the host, and no synchronization between processes in the host. I don't want them to communicate, not even in shared memory. I want someone to do that for them. So this is yet another opportunity, right, to take a very expensive operation, move the logic from a single process or multiple processes on the host to a single entity in the network that can do that for all the processes and do that in a way more efficient way. So the message is that when we talk about in-network computing, there is no one in-network computing technique. And there is not one problem that can be solved with in-network computing. There are a lot of issues and problems that can be accelerated and can be implemented in a way more efficient way if you just, break the boundary. We're very used to think about what needs to be done in software, what needs to be done in hardware, what's need to be done on the CPU, and what's need to be done in the network. And once you just, move the boundaries, do things in hardware instead of software, do things in the network instead of in the end nodes, do even things in the switches, not just in the network adapter for the nodes. Once you start looking at that as an opportunity, you can solve many problems, right? Data access for non-contiguous data, number of messages sent, you can reduce the number of messages and solve the message rate issues. In-network aggregation, you actually change the algorithm, right? It's a huge change that allows you to make a system which is way more efficient. And with that, I want to stop here talking about in-network computing. We will have a session of multiple hours on Wednesday when I'm going to dive into more details, how one can do that, and give you more insights of, opportunities and discuss in more details the hackathon. So for now, what I'm going to do is give you some time for questions. Okay, we'll start with a 10 minutes break, but then we'll come back, have times for questions. After the questions, I'm going to spend 5 minutes again to discuss the hackathon, the competition projects, and we will adjourn for today. So 10 minutes break. Okay, let's make it easy. Let's all adjourn at, let's all meet at 5:10. 10 minutes after 5, you will have time for questions, and then I'm going to spend a few minutes talking about the hackathon. Okay, so I'm back. As I said, I'm going to start with answering questions. I already have one in the chat. Please feel free to ask more questions and I'll do my best to answer. I see there are a few more. Okay, let's start with, where was it? There was a question about switch doing reduction. Well, there were two questions. One of them is, can the switch become the bottleneck? And the answer for that is easy. If you design the switch in the right way, you know exactly the how much bandwidth the switch need to absorb. You know how many ports the switch has, you know the data rate of each port, and if you implement this in-network computing hardware, by the way, it's being done by hardware in the switches to really be able to do that in the rates that are required, you can easily, or you can build this aggregation logic to withhold the bandwidth of all ports. If you look at today's existing implementation of this kind of technology, by the way, it's as of today only implemented into InfiniBand switches. We'll discuss more what InfiniBand means and how it's different from Ethernet, but it's implemented into InfiniBand switches, and today's implementation can withhold the bandwidth of all ports, so it's not a bottleneck. There was another question about switch. Where is it? Let me try and find a question in the chat. Can I? No, this is not what I was trying to do. Unfortunately, we have this noise of messages from some AI assistant. I don't see the second one. I had it before. Okay, I'll go to the latest questions. Let me see if I can.
Okay, this is
Give me
1634 the time. It's from I'm wondering whether the switch will do the reduction while it is receiving the data.
Okay.
That one, right?
Okay, so the other question is how exactly the switch does that, right? First, in order to calculate the average, the switch needs to get data from multiple sources. So if only one source sends the data, the switch will have to keep this data, and it can only process and calculate the average when everyone sends the data. So it requires some logic in the switches to hold the data until it has enough data to do the math. Actually, one could implement that in two ways. One is hold a single buffer, right? If I got the data from one of the GPUs, I keep it there. If I got the data from another GPU, regardless of which one, I could calculate the average and keep the sum or whatever and keep it in the same buffer. And then it doesn't matter how many sources I have. I only need one buffer to hold the data. The problem with that now is that the order that you do the calculation, right? If you have 4 GPUs, A, B, C, and D, the order that you do the average, for example, or the sum, let's use sum, depends on the arrival of the data. So, and we all know, or we should know, that A plus B plus C plus D should have been equal to, let's say, D plus C plus B plus A, but it's not. It is equal if you use lossless kind of data representation. Since we're all using floating point as our data representation, it's not lossless. And the order of executing this plus function so the result depends on the order. And in some cases, we want to guarantee that if I run the same application twice, I'll get exactly the same result. even though the differences are on the rounding, and it's usually not important. If you change the order, the efficiency or the accuracy of your, let's say, neural network doesn't change. But in many cases, people want to make sure that if they run the application twice, they will get exactly the same result. First, for debug, you want to make sure you don't have bugs. And if you get not exactly the same result, it's very hard to compare. There are some other reasons, mostly in HPC applications, not AI, not deep learning. But I'm going to just ignore that. So the implementation, for example, of such technology needs to decide whether it holds buffer for the different sources and guarantee that it will do the calculation in the same order, regardless of the order of arrival to the switch, right? The different GPUs are synchronous. Each one of them will send the data when ready. So you don't know which one will send first. So this is one part of depending on the implementation. And the second part is, I already said that, hey, if I'm an AI application, I'm going to ask you to do averaging of vectors, extremely long vectors. It can be hundreds of megabytes, it can be gigabytes. Switches do not have buffer to hold gigabytes of data from multiple GPUs. Forget about it. It's impossible to implement. It's too expensive. There are many reasons why no one will ever build such a switch. Meaning we need a technique where each GPU doesn't send the entire vector, it sends parts of it, and the switches hold those parts until the switch can calculate and forward the data. And only then we expect the GPU to send the next part of the data. And we want to pipeline that so that eventually what you will see is that everything is synchronized. All the GPUs are sending data at full wire speed. Data arrives at the GPU, at the switch, which immediately calculate the average for the data, send the result up the tree, and receive more data. So at the steady state, I want to see data coming in at full wire speed, data going out at full wire speed, and it doesn't require any buffers, right? If everything works in a perfect way, I don't need buffers. Since the world is not perfect, and since you have some hiccups, and you every once in a while see traffic which is not the aggregated traffic, I don't know, management traffic, control traffic, some other messages going through the wire, you will see that you have those hiccups, and switches need to be able to work efficiently in this kind of environment. It requires very good synchronization between the switch and the GPU, or the switch and the network adapter, right? It's not the GPU sending the data, it's the GPU asking the network adapter to send the data for it. So the switch and the network adapter requires some synchronization, some mechanism. Basically, we can call it flow control, right? We need the switch to signal the NIC when to send more data, when not to send more data. So we need some kind of very tight flow control that enables eventually synchronizing. One switch is synchronizing all the sources. It can be tens or hundreds of sources of data that all needs to be synchronized and progress at the same time, so that you will efficiently be able to get the data, do the aggregation, send the result up the tree, or send, if you are the root of the tree, send the results down. And eventually what you want to see is streaming aggregation, data streaming being streamed into the network as the result is being streamed back at the same time. It's not that you send everything and only then the result starts getting back. I hope it answers the question. And this is eventually how switches needs to implement this kind of technology. And this is the way it is today. This is what switches implement today. Any other questions? Anyone? Any type of question? It doesn't have to be specifically on what I've discussed today. If you want to know more about this week, feel free to ask me. While I'll give you a couple of minutes to ask questions, I'm going to share a short presentation again to discuss the at very high level the hackathon. Again, we will get there again. I just want to show you why we're going to do what we're going to do in the hackathon.
There are some other questions here.
Okay, let me
Just repeat this question.
Yeah, do you think communication is a bottleneck in deep learning training? Which decentralized communication architecture with decentralized is a much lower percentage of training than forward and back propagation? Okay, so I'll start with this question about whether communication is a bottleneck. The answer is yes. Communication still is an issue. And you know, it's kind of a race. Still, you have to synchronize the different processing engines. Still, you have to do multiple types of parallelism within the network that requires different types of communications. And what happens is that you keep getting your processing engines to run faster, right? You do buy a new GPU, which is faster than the previous one, meaning the GPU now consumes more data in less time, meaning now you need to make sure that you match the networking to that. Otherwise, hey, if you buy a new GPU but feed him with the same rate of data, it will not be able to do anything faster, right? Eventually, you need to always balance the processing power that you have within the node with the communication speed. Again, I don't like the word speed, but with the techniques to feed the GPU with the data, it's not always just speed. We showed a couple of cases where speed is not the solution. New technique is the solution. Changing the algorithm is the solution. But the answer is we're getting faster GPUs, and without feeding them with the amount of data they need for crunching, we will not be able to benefit from the speed up in the processing engine speed. So this is at very high level the answer. We talked about switch computational power. If you match that to the switch bandwidth, it's not a problem. What do you think of the Ultra Ethernet Consortium and the future of Ethernet? Okay, I probably have two parts to the answer. First, I believe that Ethernet as it is today doesn't match the requirements of large AI clusters. So I think that, you know, working on extending the Ethernet capabilities is extremely important. I think that, as always, doing that as a consortium instead of, you know, each company doing their proprietary technology, I think it's great. I think that companies working together to try and enhance Ethernet to where it needs to be to you know, match the requirements of these new applications, the AI applications. I think it's extremely important. It's a new consortium. I really hope it will be a successful one. I've seen multiple times people trying to put things on top of Ethernet and failing. I've been involved in some of those consortium activities. Fiber channel over Ethernet is just one example of a great consortium with extremely important technology that never happened. So I'd add to that, you know, as I said, I think Ethernet is not ready. I think extending Ethernet, working together as a consortium on defining extensions to Ethernet to try and close the gap is extremely important. I don't try to see that to predict the future, so I don't know what's going to happen with the Ultra Ethernet. I think that building a consortium on top of this kind of ecosystem is hard, and hopefully it will be very successful. And by the way, I believe we will see back to this ultra Ethernet. Ethernet is a very interesting technology. And one interesting thing in Ethernet is that it is looking around and looking for technologies from other networking technologies, like InfiniBand and like others. And it used to take the good ideas and try to get it into Ethernet. One thing that it will need to do is to do that faster in order to be able to match the requirements. I think that Ethernet has been moving too slow for decades. The main reason is that Ethernet is not just for one application. Ethernet is Metro Ethernet and long-haul Ethernet, and there are so many parts to Ethernet that it's very hard to move fast with that without breaking anything. And you cannot break anything in Ethernet. You cannot make an Ethernet that doesn't solve different problems. So we'll have to see. And now let me share a very short presentation. Let me see. Okay, so I said that we are going to work on implementing reduced scatter operation on top of SHARP, on top of this in-network computing technology that exists in the switches. And I wanted to talk about why we're going to do that, not how. Maybe I'll start at the end. Oops, sorry. Maybe before we talk about why, let's talk about what reduced scatter is. And later we talk about yet another operation altogether that we're not going to, it's not going to be a part of your competition challenge, but it's important as a part of understanding why reduced scatter is that important. We talked about all reduce, and with all reduce, what happens is that, let's take a look at those drawings first and what it means. In each drawing here, we have the before the operation. In this case, we have 4 processes. We call them ranks. It's an MPI terminology, but it's 4 processes, 4 GPUs, 4 ranks. Each one has its own vector of data, the input to the operation. So we're going to call a collective operation. The collective operation has inputs, right? Each rank has its input. And after the operation, each rank sees the output of the operation. So at the beginning, each rank had a vector of numbers, floating point numbers. Think about, imagine a long vector, let's say a 1 megabyte vector, long vector of floating point numbers. What we do in all reduce, let's say we had all reduce, is that everyone contributes its vector and receive the same result, right? The averaged or the summation of all the vectors. What we see here is reduced scatter. In reduced scatter operation, everyone contributes the complete vector, but instead of receiving all the averaged vector, each process, each rank only get one part of the result, of the reduced result. In this case, let's say we do sum, and rank 0 gets a quarter. It's a quarter of the results only because we have 4 processes. If we had 100, each rank, each process will get 1 to the 100 part of the completed averaged vector. So in this case, we have 4. Each one contributes its data and receive a quarter of the result. This is reduced scatter. So everyone contributes a vector, we calculate the reduction, and we scatter the result between the different ranks, between the different processes. This is why it's called reduce scatter. You reduce the vectors, the complete vector, but the result is being scattered so that everyone gets only a part of the result. It is accompanied with a different operation, which is called all gather. In all gather, what happens is that everyone contributes one part of the data, and everyone gather the data from all the sources to a complete vector. Okay, it's kind of the opposite. If reduce scatter is scattering the result, all gather is gathering results from multiple sources. It's not exactly the opposite, because in reduce scatter, you actually reduce, you actually do some calculation on the data. In all gather, you just gather the result. It's nothing but gathering data from multiple sources. So now I want to go and say a few words about why we need reduce scatter and all gather. If you're an expert in AI training, it's probably you already know that. If it's new to you, it's very high level abstraction of deep learning training flow we start with a single GPU and then we will go to distributed. So let's start with a single GPU. It's really a very high level abstraction. What you do is in a loop, you calculate gradients. You do stochastic gradient descent, right? Gradient descent means let's look at the error function, find where we are on the error function, and calculate the gradient of the error function in a way that if we move on that direction, we will get to a point where the error will be lower. And we do this calculation. After we calculate that, we actually go to the function and we move ourselves in the function. We do that in neural networks by adding the gradients to the weights. So we take one step toward the lower error on the function. Again, it's standard gradient descent. Hope everyone is somewhat familiar with that. If not, we can spend some time later this week on going through that if there are enough people that would like to get more information here. This is the standard way, and when I say update the network weights, there are multiple ways. You can just add the weights, multiplied with some learning rate, right? You want to make small steps or large steps. You can have learning rate that changes based on multiple functions. You can have momentum get in there. There are techniques to do this stage, but it's the stage that you take the gradients and you update the weights, the parameters, and it's called the optimizer. And you keep doing those two steps in a loop until eventually either it doesn't help anymore, right? You cannot decrease the error anymore, or until you're happy with the results, right? You say, hey, it's accurate enough, I'm done. This is the training, really at the highest level of abstraction I could do. The problem is that we already said we have tons of calculation to do. We have very large neural networks. We have huge amount of data to feed in the network to do the calculation. It would take ages to just train a neural network. We need to run faster. So the first technique for parallelism, it's not the only one, and we're not going to discuss the others today, but the basic technique to make it faster is to buy multiple GPUs and do parallelism. And the easiest parallelism technique is called data parallelism. This is where each GPU sees exactly the same neural network model with the same parameters, same everything. You just copy the neural network into multiple GPUs, multiple processing engines. But now what you do, instead of feeding all the data to a single GPU, you shred the data into batches, and each GPU now only see a portion of the data, meaning that each GPU has less calculations to do, and the sum of all GPUs, they see all the data. So we do parallelism based on the input or the training data. Now, what happens to the flow is that you need to do gradient descent, calculate gradients on each GPU based on the part of the training data that the GPU sees. The result here will be that each GPU, since it's using different inputs, it will have different gradients. But eventually we want to train a single neural network, so we need a single gradient vector. And here, I'm sorry, but you'll have to believe me that from a mathematical point of view, calculating the average of the gradient vectors that each GPU has is exactly the same as going back and doing everything on a single GPU. It's exactly the same result as, and I'm not going to do all the math to prove that to you. So we need to calculate the average of all the gradients. We already said that, and update the weight. So calculating the gradients is actually an all-reduce operation. We can do that with Sharp. We can do that with whatever you want, right? This is the process that needs to be done, and this allows us to do data parallelism. We took a problem that could run on a single GPU. We now use parallelism. It will run faster, and it requires this all-reduce phase. It's a new phase. Now, the problem with that, it's a great method, right? But the problem is that if we look at the work that we do, basically, when we calculate the gradients, each GPU sees a different set of inputs, so it makes sense that they work in parallel. When we do all reduce, we calculate the averages. But now we have this stage of updating network weights, where each GPU has exactly the same copy of the neural network, exactly the same copy of the averaged gradient vector, and they're doing exactly the same operation. And you know, with the growing size of neural networks, those vectors are very long. And even this kind of simple operation of just updating the neural network, but it's based on a very long vector of gradients and very long vector of weights, it's expensive. And we do that in an inefficient way because each GPU is doing exactly the same calculation, the same inputs, same outputs, same operation. So what we could do is say, okay, let's do what we call distributed optimizer. What a distributed optimizer means is that instead of each GPU doing the same exactly, we go to a new technique called distributed optimizer, where we start with the gradient descent. Each GPU sees the neural network and a different set of inputs, calculates the gradients. Great. Now, instead of doing all reduce, what we do is reduce scatter, so that each GPU now only see a portion of the average gradients. Okay, it doesn't see all the vector. It can update only a part of the neural network. It cannot update all the neural network, but each GPU updates now a different part of the neural network because each GPU has a different part of the averaged vector. And now what we have to do is eventually I want all the updated network. So I need to gather the parts that I didn't calculate, me as a GPU, right? I'm one of the GPUs. I got, my portion of averages. I fixed this part of the neural network. Now I need to gather the updated parts from the different GPUs that did the same, but they did update the different part. Each GPU updated the different part of the neural network, so that eventually, when I gather all the parts, I have the updated neural network. And now what happened is that each GPU needed to update only a part of the network, of the neural network. So I parallelize the optimizer as well. This is why it's the distributed optimizer. And now if you look at what we need here, we need two networking operations. And instead of just all reduce, we break the all reduce into reduce scatter of the gradients, and later all gather. But notice that this all gather is actually gathering not the gradients, but the updated neural network weights. So with the reduce scatter and all gather, we actually allow the GPUs to do less work. If we can do reduce scatter and all gather in an efficient way, which needs to be as efficient or close to as efficient as the optimized all reduce, right? Before that, we did the optimized all reduce. We save work for the GPUs. So by moving from all reduce to reduce, scatter, and all gather, we save a lot of work for the GPUs. It's not trivial, even though it's just updating the neural network. If you look at the time it takes, it is not negligible. So moving to reduce, scatter, and all gather communication patterns, collective communication patterns, we save a lot of work from the GPU and we can accelerate AI applications. So again, we will focus on reduce, scatter in this competition. We will leave all gather for a different time, just because we want you to focus on one problem. It's not an easy one, but this is the part of the picture where you're not just it's not just and we didn't just choose a collective communication pattern and say, okay, let's see if you can optimize that. It's something that large companies building large AI systems are trying to solve today. It's not one company, there are so many companies trying to build large systems to do large language models, to run them in an efficient way. There are huge models with hundreds of billions of parameters. Some models have trillions of parameters. It requires huge amount of processing power, and eventually it can be doing that in an efficient way can change the way we do that, and can change from it's impossible to, hey, I can do a trillion parameter neural network and train that in reasonable time. Still, training a large language model is expensive. You need a large amount of processing engine. You are crunching huge amount of data. Saving compute power by doing distributed optimizer is extremely important, and it cannot work if if you do that, but you reduce, scatter, and all gather are not efficient, you just lose everything that you want by distributing the algorithm into networking overhead. So we must have reduce, scatter, and all gather running in an efficient way to allow this kind of optimization. This is for the competition this week. With that, I'm done with the slides. Again, if we have more questions, I'll be happy to answer. I'll be with you during this week, so you don't really have to ask everything now. You can ask later, you can ask tomorrow, and you will have, as I said, an amazing list of instructors this week. Ask questions, not just me, and you'll get great answers. Okay, let's wait one more minute. If you have questions for now, I'll answer that now. If not, you can still use the chat. And I'll answer either through the chat or tomorrow.
Hi, Gil. Can you hear me?
Yes.
I do have a question relating to the coding part. Like, will we be providing the servers to get hands-on practice?
So during the week, we will have hands-on practice with the instructors being with you and giving you support. And specifically for the competition, I'm not sure I have the answer, but yes, we will have hands-on, and we will have systems to access, and you will have support from the team to do hands-on.
Yep, that's great. Thank you.
Okay, so I'm going to mute myself, and try to follow the chat. And again, I'm going to be around all week, so feel free to ask more questions either now or later. And I really want to thank every one of you for joining, and wish you a very successful week. I think it's an amazing opportunity coming from the HPC Advisory Council.
There's another question.
Okay. And for today talk, I wonder what is the, I have this. What is the size of problem we are going to solve? It's a good question. I don't know. We will need to figure out the system size, and based on that, we will define, the system size you have access to, and based on that, we will define the data sizes and the exact benchmark that you need to run. Probably someone else from the team already knows. I don't. So we will provide all those details.
Right.
Okay, if there's no new question, let's thanks for Gil. Thank you, Gil, for today's great presentation. So everyone, let's meet tomorrow. Tomorrow we will start from Beijing time, 9 a.m. Okay, bye-bye.
Recording stopped. Recording in progress.